Hi guys, Blackbox here. Another tutorial video for the FSLabs A320-X. And today I'll be talking about the pneumatics and the pressurization of the A320-X. I'll first cover the basics regarding the bleed supply and all the ECAM symbols that you can have a look at on the bleed symbol display. And after that, we'll be doing a flight from Athens to Tirana, and I'll be showing you different flight phases, also with regards to how the pressurization system behaves. So let's get straight into it, and let's have a look at the bleed schematic. Now, in order to be able to pressurize the cabin of the Airbus, you will need a high pressure bleed air source. And this comes from two stages of the compressor of the engine. One is the so-called intermediate pressure stage, and the other one is called the high pressure stage. Usually the intermediate part pressure will be enough to pressurize all the necessary systems. However, if bleed demand is very high or the RPM of the engine is somewhat low, then the high pressure valve will also open in order to meet the bleed demand by the systems. Now, bleed air coming out of the engine is very highly compressed, and so as physics has it, if you compress air by a great deal, then it becomes very, very hot. Usually you will have temperatures exceeding 300 degrees Celsius. And so this hot air has to be pre-cooled in order to be used by the different systems. And in order to do this, you actually extract cold fan air, and the BMC, the bleed monitoring computer, will actually regulate the amount of fan air which goes into the pre-cooler by a regulating valve. And so when the bleed air comes out of the pre-cooler, it usually has a temperature around 160 degrees Celsius and a pressure of 30 psi. From there, the bleed air will then be used for wing anti-ice, also for the packs, and some of it goes into the cargo heating, and also you will need the pressure to pressurize the hydraulic reservoirs. Of course, the engine bleed air isn't the only source that you can have. There could be a so-called ground air supply connected to the aircraft, and also the APU obviously will be able to supply bleed air for the different systems. Now next, let's have a look at the bleed system display. And on this display, you have a lot of information. So let's start right at the bottom left there. You have the letters IP and HP, and those correspond to the intermediate pressure and the high pressure supply from the engine. You have a high pressure valve. Usually, if the pressure from the IP, the intermediate pressure, is enough or high enough, then this valve will usually be closed. Now, just above the IP, you have the indication for the engine bleed valve. And if it's in line, obviously the bleed valve is open and supplying the different users like the wing anti-ice, the Peck system, etc., etc. Above the engine bleed valve, you have a so-called pre-cooler outlet temperature indication and the pre-cooler inlet pressure indication. So in this case, the outlet temperature of the left bleed pre-cooler would be 165 degrees Celsius and the pressure at 24 psi. Further upstream, next in line, is the so-called Peck flow control valve, and that is indicated from a scale from low to high. And depending on the Peck demand, this valve regulates the amount of bleed air going into the Peck system. Just above that, you have the Peck compressor outlet temperature. Now, I'm not going to go into how the Peck itself works. I might do that at a later stage, but for now, just have to accept the fact that this temperature indication is the Peck compressor outlet temperature. Next in line, you can see the so-called Peck turbine bypass valve position. Again, this is within the Peck system. That is just now an indication between C stands for cold and H stands for hot, so the valve fully open at H. And then above that valve indication, you have the Peck outlet temperature. So as you can see here, the bleed SD page actually also shows some information regarding the Peck system. Before we move on, there's some more indicators here. For example, you have the ground high pressure connection indication. Then you have the position of the cross bleed valve. We'll get into that later in this video. And then further up, you have another indication for the ram air valve. This I won't be covering in this video because this system is mostly used in an emergency case. All right, let's now get into the practical side of the bleed system and its operation. All right, so here we are in the cockpit. We've selected the bleed SD page, and right next to it we can see the air conditioning panel. At the moment, the bleed system is fed by both the intermediate and the high pressure valve, and that is because we're pretty much at idle power at this stage. If I increase the power and we pass about 45% and 1, you'll see the high pressure valve closing. There it is. And so now the intermediate pressure being supplied from the engines is enough to supply all the users of the bleed air. As the thrust is reduced, the high pressure valves open again to help out with the bleed demand from the systems. Alright, so let's now switch off one of the engine bleed supply switches. And I'm going to switch off the engine 1 bleed switch. And you can see immediately that the engine bleed valve closes and also the high pressure valve closes as well. And since there is no bleed air now going to the Peck system of the left side, the Peck control valve will also close automatically. Next, let's have a look at the cross bleed valve. There's a cross bleed valve selector with the positions auto, shut and open. Now on the auto position, the cross bleed valve will open automatically if the APU bleed switch is selected to on. The cross bleed valve will close if the APU bleed valve is closed, or in case there's a wing, a pylon or an APU leak. Now the position shut in this moment doesn't do anything because the cross bleed valve is shut already. But if you select the switch to open, then you will force the cross bleed valve to the open position. Now you've connected both the left and the right bleed system. If you switch it back to auto, obviously the valve will then close again and separate the left and the right bleed system. Another example, if engine 1 bleed is off, opening the cross bleed valve manually will again connect the left and the right bleed ducts, and hence you have, for example, all the packs supplied. And of course, for example, now you can do an engine cross bleed start. Right, next we'll add some APU bleed. Now switching on the APU bleed, we'll do several things. First of all, the engine bleed valves close, and then the cross bleed valve opens, and so the APU bleed now supplies the whole bleed system. Now when you select the cross bleed selector to the position shut, then in this case you will force the cross bleed valve to close position, and hence separating both the left and right bleed duct system. And of course, when we switch it back to auto, then the cross bleed valve will open again. Now the FSLabs A320-X has a push button called Hot Air. Now this push button, if switched to off, closes the hot air trim valve or hot air regulator valve. And the hot air regulator valve regulates the pressure of hot air, which is tapped upstream of the packs. And this is used in order to optimize the temperature regulation in the cabin. Now usually you would not touch that button, it would always be on in order to optimize the air conditioning. However, there might be a duct overheat fault or a valve fault, and then the procedure would have it that you switch the hot air supply off. And as you can imagine, the cabin will become somewhat colder, and in real life that will mean that you might even need to descend to lower flight levels or even do a precautionary landing somewhere en route. But like I said, usually you would not touch that switch. However, I'm sure some of you have been wondering what this is for. Another interesting switch you will find in the air conditioning part of the overhead panel. It's the Peck flow control switch, and you have three settings: low, norm and high. So this switch permits the selection of the Peck valve flow, and that is according to the number of passengers and ambient conditions. So low would be about 80% of airflow, norm obviously 100%, and the high setting would give you 120% of airflow. Now the setting low would be used in case you have less than 115 passengers, and this saves up to 0.5% of the trip fuel. The selection high would be used in case you have abnormally hot outside temperatures or very high humidity outside in the cabin. The last switch I would like to talk about is the ram air push button, and this actually activates a little ram door on the left lower side of the fuselage. Now this push button is only to be used in an emergency, and you have to be careful because the differential pressure has to be less than 1 psi. Now once you push the switch to on, you'll see on the bleed page the ram air valve opening, and hence supplying the cabin with outside air. Now in the inside view you can see the ram air flap being open now, and scooping air, if you like, which is then transferred into the cabin, bypassing the Peck system. Obviously switching off the ram air supply closes that flap again. Alright, let's start up the engines, and you'll notice that when you select ignition start, the Peck valves will close immediately, automatically, and hence the full bleed pressure from the APU is available for engine start. Now after engine start, say the engine 2 is started and running at idle, if you don't start the second engine immediately, after 60 seconds the Peck valves will actually open again automatically. Both engines are now started, and as I said, after a while, without touching anything on the conditioning panel, you'll see that the Peck valves will open again automatically, supplying the packs with APU bleed air. Now remember, as long as the APU bleed valve is still open, the engine bleed valves close automatically. And so the after start flow starts by switching off the APU bleed air, and then switching off the APU, and then once the APU bleed air is switched off, the engine bleeds will take over the bleed supply for the air conditioning packs. Let's now talk about the pressurization system of the A320X. Now when you start up the simulator, you've come across the message cabin pressure landing elevation fault, and that is because there's no arrival airport inserted into the FMS. So once that is done, you'll see the message disappear. And that is because now the FMS has a destination airfield and hence the destination airfield elevation. And so it can calculate the proper pressure that it needs to set once you land at that destination airport. Now the nice thing about the pressurization control in the A320X is that it is fully automatic. So you've inserted a departure airport, a destination airport, the flight level you're going to fly at, and so the FMS and the pressurization computer can now calculate a proper vertical flight profile. And that looks like this. So after you've started the engines and taxi out to the runway, and even after lineup, the outflow valve is still fully open. And hence the differential pressure in the cabin is 0. And that is quite convenient because in case of an emergency where you would have to evacuate the aircraft, the doors can be opened without any problems. And so once you start the takeoff roll at a certain speed, the outflow valve starts to close slowly. And that is simulated quite nicely by the FSLabs A320. You can see the outflow valve closing ever so slightly. It's not closing completely, it's just closing enough to slow down the outflow and hence pressurize the cabin. You heard me correctly, it is pressurizing the cabin, i.e. the differential pressure is actually getting negative. And that is to avoid pressure surges which will happen during acceleration and the climb phase. Now after liftoff, the main landing gear becomes decompressed, and that gives a signal to the pressure controller to start with the climb mode. From this point onwards, the cabin altitude will vary according to a calculated profile, which is then influenced by the vertical speed of the aircraft. You will, of course, notice the differential pressure slowly becoming bigger and bigger during the climb. Now, the normal vertical speed climb rate of the cabin is usually 400 feet per minute, while in the descent later on, you'll see that it is about 500 feet per minute. At the moment we're passing 20,000 feet, you can see the differential pressure is at 6.6 psi and the cabin altitude only at 2,600 feet, which means it's still very comfortable for the passengers on board regarding the pressure of the air. If the aircraft does a level off on the way up to its cruising level, then the cabin altitude will also stop its climb. Here the aircraft is just about to level off at level 230. And shortly after the level off, you'll see the vertical speed of the cabin become a 0. And of course, as soon as the aircraft starts a new climb, the cabin vertical speed will also increase again. Now passing 30,000 feet, we can see the cabin altitude is reaching 5,300 feet and the differential pressure is at 7.7 psi. Now at cruising level, or the highest cruise level, 39,000 feet, we have about 8 psi differential pressure. Now the maximum differential pressure is 8.6 psi. At that point the safety relief valve will then activate and let out pressure from the cabin. Also quite typically at 39,000 feet the cabin altitude is at 8,000 feet. Alright, we're already starting our descent, and now obviously the opposite happens to the climb. We get a vertical speed negative rate, usually around minus 500 feet per minute, and that way the cabin altitude will obviously descend as well, and the differential pressure will then slowly decrease. Alright, passing 29,000 feet, you can see that the differential pressure has dropped down 7.4 psi. Still have a stable descent rate at 500 feet per minute on the cabin, and the cabin altitude now is at 5,400 feet. Again, this descent schedule is controlled by the cabin pressure controller, and that is fully automatic. And coming up to 20,000 feet, differential pressure 6.2 psi, and the cabin altitude now at 3,700 feet. Alright, let's quickly have a look at the cabin pressure chart again. And during the descent, the FMGCs compute the time until touchdown. And so the cabin pressure computer continually changes the cabin altitude until the landing. And this is where the landing field elevation comes into play. You'll find that information, for example, on the cabin pressure page. On the top right corner, it should say auto and then something in feet. In our case, it's 100 feet. The cabin pressure controller will then try to reach a cabin altitude of about 200 feet below this landing elevation. And this is again for passenger comfort to avoid pressure surges in the cabin during landing. Should it become necessary at some point to quickly descend, for example, you're high in the profile and you want to descend with the speed brakes, the cabin pressure controller will notice that and adjust the vertical speed of the cabin accordingly. And this is again to make sure that the profile for the cabin is such that it does reach those minus 200 feet below landing elevation during the approach. Now, if the cabin pressure controller decides that the cabin is still behind the schedule and you're doing a level off, like we're doing here at 7,000 feet, the cabin will still continue its descent until it reaches the optimum profile again. So a very clever system. And so once it does reach its optimum profile, then the cabin vertical speed will also go to zero during level flight. Now we're getting close to the final descent, and at the moment you can see differential pressure is only 1.8 psi and cabin altitude at 300 feet. And so from here only small adjustments are necessary for landing. Alright, so now we're at short final, and we can see that the cabin altitude now is at minus 50 feet. And so it's almost at the 200 feet below the landing elevation of 100 feet. Okay, so now let's have a look what happens during touchdown and the rollout phase. So after the main landing gear touches down, the cabin pressure controller goes into ground mode. And then the controller slowly opens the outflow valves. And so you can see that the vertical speed of the cabin now is obviously increasing, and the cabin altitude will match the 100 feet landing elevation, and hence the differential pressure now is zero. And so now the doors can be opened since there is no residual pressure in the cabin. Alright, so we come to the end of this video. It's gotten quite long, almost 25 minutes. And so I'll do another video, and in that one I'll be explaining a little bit more about malfunctions of the cabin pressure system. Alright, so thanks for watching. If you have any questions, post them down in the comment section below. Until the next time, as always, happy landings.